Hi students, in previous class we completed regarding the photoelectric effect including the calculations, and now another important part in atomic structure, that is nothing but hydrogen spectrum. So first of all, it is an example of emission and line spectrum. That means, as you know, the types of spectra what we are having, that is absorption and emission. In emission we are having line spectrum and band spectrum. So it is one of the best and the simplest line spectrum under that emission category. So whenever if you heat hydrogen gas in discharge tube, here what will happen? Hydrogen molecules, they are going to dissociate as atoms. So now the electrons present in those atoms, they are going to absorb energy and they are going to excite into higher levels by depending upon the amount of energy that they absorb. After that, they are involving in de-excitation. And here one thing you have to remember, de-excitation it may take place either in single step or in several steps. So whenever the electron is de-exciting from higher level to lower level, it is emitting certain amount of radiation, and that radiation is in the form of light as per photoelectric effect that was generalized by Einstein. And if you introduce that light through the prism, definitely it is going to be dispersed in different radiations, and they are responsible for a specific line on screen. So that impression is what we call as spectrum. And now if you observe this diagram as far as hydrogen spectrum concerned, suppose if electrons are excited into 7th orbit, now if they are re-excited into first level, that energy is responsible for a specific line on screen. Similarly, from 6th to 1st, or 7th to 5th to 1st, 4th to 1st. So like that, here the de-excitations are going to take place by the electrons. And now, if you observe that hydrogen spectrum, in this we are going to observe mainly 5 series of lines. They are nothing but Lyman series, Balmer series, Paulsen, Brackett and Fund series. Of course, there is 6th one, Humphrey series. I think up to +2 level not necessary. And here, if you observe Lyman series, when we are going to get Lyman series, see this diagram. Any electron from excited state, if it is de-exciting into the first level, whatever the lines that we are getting, they are nothing but Lyman series, and these Lyman series, they are formed in ultraviolet region. So series and region, it is one of the important point what you have to remember. And next, if you observe Balmer series, if electrons de-excite into the second level, so there we are getting a series of lines which are present in visible region of electromagnetic spectrum. Like that, into 3rd orbit, Paulsen, 4th orbit, Brackett, 5th orbit, Fund, and all these they are in infrared region. Of course, this is at near infrared, mid infrared and far infrared. So like that, here we are getting different series of lines in hydrogen spectrum. And now here, as far as the diagram concerned, one thing it is very clear, that is name of the series and number of the orbit into which electron is de-exciting, and then name of that region. So if electron is de-exciting into n equal to 1, means first level Lyman series in ultraviolet, second level Balmer series visible, third level Paulsen series infrared, fourth level Brackett series infrared, fifth level Fund series infrared. So like that you have to remember the series and the region. That is the fundamental explanation as per the diagram. But now, if you observe Balmer series, since it is in visible region, so he proposed one equation to find out either frequencies or energies or wavelengths or wave numbers for each and every line in his series. So for that, here first we will see that Balmer equation and its importance. So now, if you observe this Balmer equation, here it is nothing but nu bar, means wave number, which is equal to 1 by lambda, that is equal to r into 1 by n1 square minus 1 by n2 square into z square centimeter inverse. So that is what we call as Balmer equation. And now here r is nothing but Rydberg constant. Its value, that is 109,677 centimeter inverse. Since we are mentioning centimeter inverse wave number. And what is N1 and N2? See, if you observe any series, suppose Balmer series, we are getting the lines in Balmer series where electron de-excited into second orbit. Now, it may be from third, fourth, fifth, sixth or seventh. So thereby, here if you observe N1 and N2, N1 is nothing but the number of the orbit into which electron is de-exciting. Whereas N2 is nothing but the number of the orbit from where the electron is coming. So like that, for any series we can use this expression. But now, if you observe Balmer series, by using this equation, he calculated the wavelengths present in his series. So for that, so be clear about this expression, and since it is applicable, we are going to apply for hydrogen, no need of Z. But for any other elements, we can use its atomic number. And now, as far as Balmer series is concerned, see, just for your understanding purpose, I am giving a simple diagram only for Balmer series. So this is nothing but to second orbit. Let it be N1. This is N1 for Balmer series. And now higher energy levels. Now see that first line, if electron is de-exciting from third to second, see, this is the line what we are getting, where here it is nothing but N2, which is equal to 3. So 3 to 2. So this is the first line in Balmer series, which is represented by H alpha. Like that, 4 to second. Here let it be N2, that is 4. 5th to second. So in this way, we are having different lines. 6th to second, where N2 is considered as 6. So here the first line is H alpha, second line is H beta, third line H gamma, and fourth line H delta. Like that we are getting. And now he calculated the wavelengths of these lines with the help of his equation. And one more important point here what you have to remember. See, this is the line where we are getting an electron de-excited from third to second, fourth to second, fifth to second, sixth to second. And in any series, there will be one line where we are getting, if electron is de-exciting from an infinite orbit, means we don't know from which orbit it is coming. So here also we are getting one line. This is what we call as H infinity. Okay, so here N2 will be considered as infinity. That is infinity. So in that way, in Balmer series, we are having different lines. And now, with the help of his equation, he calculated the wavelengths. They are found as, here first line, in angstroms I am giving 6563 angstroms, 4861 angstroms, 4340 angstroms, 4101 angstroms, and this is 3647 angstroms. So like that we have different wavelengths in Balmer series. So this indicates, since it is the first line and it is the last line, that means in Balmer series we have the lines in the range of their wavelengths, that is 6563 to 3647. Means there is no any line whose wavelength is less than 3647 in Balmer series, and there is no any line whose wavelength is greater than 6563 angstroms. So that is the meaning of this diagram. So be clear about these 5 values. Direct questions are there based on the wavelength of first line, wavelength of second line. Then without calculation you can go for it. And here if you observe this last line, so in this last line N2 is infinity. That means this is the least or minimum wavelength in this series. So in any series, the minimum wavelength what we are observing, this is called series limit. Series limit. So in Balmer series, series limit is 3647. And after that I will give the expression how to find out the series limit in each and every series. So now this is regarding the different series of lines and especially related to Balmer equation. So now finally, if you want to apply that equation for Lyman series, see this, we have different lines. For all these lines, N1 equal to 1, N2 will be different. Similarly, in Balmer series, for all these lines, N1 is same, that is 2, whereas N2, that will be different. That means, in any series, either line 1, Balmer, pause, bracket and front, means in a series, the value of N1 remains same, N2 will be changes. And here, according to this diagram, if you observe one important point, 3 to 2, we are getting 6563. Infinite to 2, 3647. Means, if N2 is nearer to N1, whatever the line that we are going to get, its wavelength is maximum. Means energy is minimum or frequency is minimum. Whereas, if N2 is far away from N1, then wavelength is minimum. That means energy is maximum. So, here to get maximum wavelength in any series, not only in Balmer series, in any series, to get maximum wavelength, N2 should be nearer to N1. N2 should be nearer to N1. Since it is maximum wavelength, that means we can say that minimum energy or minimum frequency. So, in a series, to get either maximum wavelength or minimum energy and minimum frequency, N2 should be nearer to N1. Whereas, here, if you want to analyze the diagram, to get minimum wavelength, N2 should be far away to N1. It should be far away to N1. So since wavelength is minimum, here both energy and frequency, they are going to be maximum. So this point you have to remember, because sometimes they will show the electronic transition, in which transition maximum energy is releasing or maximum wavelength is releasing. So to answer that type of questions, just you have to remember these 2 points. So finally, as per this, in a series, to get maximum wavelength, N2 and N1 should be close. And to get minimum wavelength, N2 should be far away from N1. So like that, here we have different lines in Balmer series, and once again be clear about these values in angstrom. And in any series, if N2 is considered as infinity, whatever the wavelength of that line that we are observing, it is nothing but its means that series limit. So in Balmer series, series limit is 3647. Okay, so that is regarding the fundamental analysis of this hydrogen spectrum. And now we'll go for different formulas related to this. For that purpose, first we'll go for series limit. Just now, as I said, in any series, if n2 is considered as infinity, so then here what will happen? 1 by lambda infinity, that is nothing but r by n1 square into z square, because n2 is infinity. Therefore, wavelength of that infinite line is nothing but n1 square by r into z square. So this is the formula to find out series limit of any series. So for that purpose, in Lyman series, what is the general expression for series limit of hydrogen atom? 1 by r. And for Balmer series, 4 by r, because n1 is 2 for Balmer series. So like that, if there is any question related to the general expressions, just substitute n1 value in that formula. Okay, so this is regarding series limit. And another one, generally, sometimes you have to find out frequency of the emitted light. See, for example, this is Balmer series, first line, H alpha. What is the frequency of the light emitted when electron de-excited from third to second, or fourth to second, or second to first? So in that way, they used to ask regarding frequencies. So for that, if you have the internal relation, means here frequency. What is frequency? Frequency is nothing but C by lambda, or that equal to C into nu bar. But already you know that nu bar. So therefore, frequency nu equal to C into R into 1 by n1 square minus 1 by n2 square. Here I am not mentioning Z because our entire discussion is related to hydrogen spectrum. Now C is constant, R is also constant. So if you substitute both C and R values, here finally frequency of that emitted light nu equal to 3.3 into 10 power 15 into 1 by n1 square minus 1 by n2 square into z square. But here no need. So this is the formula to remember for the calculation of frequency of emitted light. Direct formula. So no need to go for nu bar first or wavelength. Directly in this expression, just substitute n1 and n2 values. Similarly, energy. See, here energy equal to h nu. Already you know that nu. Now just substitute h value. So here it will becomes 2.18 into 10 power minus 11 into 1 by n1 square minus 1 by n2 square x in x, means in CJ system. Whereas if you want to express in joules, the same expression becomes 2.18 into 10 power minus 18 into 1 by n1 square minus 1 by n2 square joules. So that is the direct formula to find out the energy of radiation emitted if electron is de-exciting from n2 to n1. So like this, with the help of that Balmer equation, we can find out not only wave number or wavelength, we can calculate the frequency emitted or energy emitted. Of course, whatever the energy released, that is nothing but the energy difference between the two orbits. So, whatever the energy here we are calculating, it is nothing but delta E, means E2 minus E1. So, sometimes you have to find out the energy difference. So, for that, even though we have different formulas, With the help of Balmer equation also we can find out the energy difference between the two orbits. So this is another extension for that Balmer equation. Okay, and after that, another important concept. This is all general information. But now we'll go for the simplest way to answer the questions what we are going to get in objective examinations. So we will see that in next class.